student in the middle of work, which is related to my long year quest to do something like epsilon expansion for turbulence, like what Wilson did for equilibrium phenomena. And let me remind us that for this, we're actually looking for something which is turbulent and yet close to Gaussian statistics. And well, the natural candidate is with turbulence, as a maybe comment in the end, and as we found recently with Michal Shavit, is actually not a good candidate. So the whole statistics of weakly interacting set of waves is not close to Gaussian, even though the statistics of any single wave is close to Gaussian. So what instead we're now doing in parallel is what Michal talked yesterday, and so I'll continue her talk, is this model which goes back to this Arnold idea that incompressible fluid is like a rotator. So just a vector rotates transversal to itself, and it's generated the whole industry of shell models. And what we'll be considering here is a particular case of shell models, which is more or less like what is shown below, is a set of resonantly interacting waves. So it's a shell model, but which is also Hamiltonian dynamically. And then we add random forcing, and then we add dissipation, and but this, because it's from the same family like Euler equation for solid body and Euler equation for incompressible fluid, it has this particular property that thermal equilibrium is exactly Gaussian. Moreover, thermal equilibrium is Gaussian with non-interacting modes. So the probability distribution is a direct product of probabilities of Gaussian for every mode. And so we naturally were looking, as Michal explained yesterday, to the case where turbulence can be close to it. And turbulence, of course, is something which is apparently non-Gaussian because it must have a flux. So it must be a short cumulant which breaks time reversibility, and it's definitely non-Gaussian. And yet, if we consider this equation and we assume that this coefficient of interaction V has a scaling alpha, then for alpha equal to 1/2, naively define scaling of correlation functions in turbulence coincides with that of equilibrium. And we had such situation before. There is Gross-Pitaevsky in dimensionality to share this property. There are some plasma waves. Since maybe late 70s, we know that if you have such a consignment, then your spectrum will be very close to thermal equilibrium with a small, usually logarithmic correction, not a power law, but logarithmic, namely very weak correction. And so it is also in this case, which we discovered in our previous work with Shavit and Vladimirova, which was published in PRX last year. So we were very enthusiastic that this is exactly the case where we can start epsilon expansion. So we do have a third moment, and this third moment would be either direct cascade or inverse, because it's a totally symmetric situation, which where you have turbulence coinciding. Then you can skew it this way, it will be inverse cascade, skew it this way, it will be direct cascade. Both were observed, and we see the parameter of nonlinearity, and we see that it really, if we define it as a skewness, at damping region is of order unity, but as you go into the inertial interval, it goes to 0, and as you make interval longer and longer, then you see that it's statistics of a given mode. So your pair correlation function, your occupation numbers are getting large if you keep third moment flux unity. And which means that this dimensionless skewness would be decreasing non-stop. And we were very enthusiastic. And so we started this exercise. And in particularly, we started first to see how moments, higher moments, AN, here is just amplitude, wave amplitude as raised in the power n, and relatively to its Gaussian expression. It's not a constant thermal equipartition as a function of a mode number, but it's really not a big change. You see, it's a change in between from here inertial interval starts from approximately 0.6 to 1.3. So this is a really minor change. But what is more important, all moments scale Gaussian. So when you look at amplitude of a given mode, its statistics is Gaussian no matter in which I, no matter how deep into the inertial interval you go, which is exactly opposite to what we have usually in turbulence, that as you go into the inertial interval, you see that your statistics is getting more and more non-Gaussian. Here it's a uniformly close to Gaussian for all I, as we expected, and of course, that's precisely why we choose this model. So then it would be natural to do something like to look for the probability distribution, its logarithm, as the main Gaussian term, and then to do small corrections to it, which the first correction will be cubic, because you must generate a third moment, which is a flux, but it must have a small factor in front of it, and then you would have a higher cumulance. What is important for this model, which I did not mention before, that it has gauge invariant, namely, if you just multiply every amplitude by exponent in the power I times Fibonacci number of this mode, that it would be invariant. So only it's a little bit reminds other gauge field theories and particularly confinement problems. So you see that you can have strings here where all this Fibonacci sum into the Fibonacci of this K. And so in principle, you can have such term. And then you are interested what will be the coefficient in front of it, because we would expect that because it's close to Gaussian on a level of one mode, that we're also expected to be on the level of many modes. And so we expect that the higher the M, the order of this correlation function, the smaller will be this factor. So we already found empirically that in front of this cubic moment, this factor is like decreases like 1 over size of the inertial interval. And so we were kind of looking for it, and then we are into a big surprise. So let me now describe this surprise, and I think that it actually teaches, at least it teaches me something which I did not think before about turbulence, at least not in that clear form. So again, to understand the form of the PDF, we would like to understand what would be the high order cumulance. And because we expect it to be perturbative, then we'll now write Hopf equation one by one on this cumulance. And again, only cumulance for which this sum of Fibonacci, they're actually frequencies. It's kind of a resonant condition. Okay, so you write equation for the zeros cumulant, which is the second moment, which is occupation number. You get condition on a third moment, which here it's defined like C21. It is just third moment. This just gives you flux constancy. This is a trivial zero step. Then you write equation time derivative on the third cumulant. And you, again, here epsilon is the difference from alpha 1/2. So if you take epsilon equal to 0, then you can have a fourth order moments. And then you make a natural assumption that they are close to Gaussian. Namely, you decouple them. And you indeed see that this first line, which is kind of has a reducible part, it turns into 0 for exact equipartition. But we don't have exact equipartition. We have a logarithmic distortion of the equipartition, as we have seen. So we may now assume that it has this form, and we find out that this is non-zero, but is suppressed more or less by the factor which is 1 divided by number of mode minus the dissipation mode. Because when I is of order of d, it must be of order unities, it's not non-Gaussian. But when your I is much less than your dissipation for a, say, direct cascade, this is a big number and it's a denominator. Good, excellent. So we now conclude that it must be compensated by the second line, which is fourth order cumulant. So you conclude that the fourth order cumulant are in comparison with the fourth order moment of a single mode are suppressed by this single power. That more or less what is we expected. And then, of course, as usual in the Hopf equation, you go and differentiate fourth order cumulant. And you are for a nasty surprise. There are no consolations there. You can just directly check it. And then you can actually develop a very generic procedure where you can show that at any order, an order will be called M, there is no further consolations. So all these cumulants are of the same order. So it's only, it's related to this conservation. The third moment is definitely special. So as a result, we obtain this estimate that no matter what is the order M, the respective cumulant is suppressed by the same power, not by anything which would be related to M. You can say, okay, still they are small. Yes, it's true, they are small, but the moment that you start to compute anything like relative entropy, pullback-Lebesgue divergence between your probability distribution and Gaussian, you need to sum all these cumulants, right? And each one of them is small, but they're small only like one of a number of modes. So when you start summing it over modes, you find out that it all sums out into quantities which are the Fodor unity. And another angle that you can get into this is that what we was already noticed in our first paper with Michal 2 years ago on PRL, is that if you look at the entropy production, in this case, and again, entropy here is not an entropy of a Gaussian distribution of mode. It's not additive entropy of Boltzmann. It's a Gibbs entropy of the whole mode distribution, where rho is a distribution of a multi-mode distribution, like I've shown you before. Then you find out that it has, of course, Liouville theorem guarantees that dynamical interaction conserves entropy. So you have pumping contribution and you have dissipation. And if you now plug here your near Gaussian PDF, you get that this is a very small relatively to this. This is because this is actually suppressed like one of the occupation numbers, which is again large. And then again, you see that you actually cannot satisfy this condition if your whole probability distribution is close to Gaussian. And then, of course, we went with Vladimirova to check this assumption. It's really now, we want to check a very long multi-mode correlation functions. For this, you need really long intervals. And fortunately, Vladimirova invented the trick in which we kind of renormalized our variables in the right way. And so the equation look like this. So when alpha is 1/2, the right side is independent on alpha, because the main problem in shell models is that the higher the mode, the shorter is the interaction time, the shorter must be your integration time step, and it's exponentially growing. In these new variables, it's actually uniform, and so we can really afford having very large inertial intervals, not like 30, 40 people had before, not like 80 we had in our first work, but like a few hundred, which is kind of a record precision. And then, of course, we find out that it's not really Gaussian. So when you look at the probability distribution, as I've shown before, of a given mode, it's indistinguishable from Gaussian. But if you already look at a three-mode quantity, which is the probability distribution of a relative phase between three modes, this quantity theta, right? You find out, and this is for different eyes, you see that they more or less the same. Again, direct cascade and inverse cascade had maximum of pi over 2 or minus pi over 2, because it must give you. But also, if you look at this probability distribution, it's not close to a constant, not in any way. It's really something which is totally of order unity. And then, of course, what we just, it's still unpublished results. We're now writing the paper about it. So when you look at all these cumulants, which are listed here, and also here at the right, you see the stable, and it shows you, and this is a logarithm. So you see, when you look at this cumulant, they aren't decreasing, they're actually growing very fast. That's a logarithm of them, right? even were able to get what is this, 3, 6, 8, 9. This is ninth order cumulant. This is truly heroic computation, and it's large. So again, because of this Hopf computation, let me return back. It's actually predict the dependence on mode number, and so now we try to check this dependence. So what we did, we took the respective cumulants of order m, divided it by occupation number in the power m over 2. That makes it dimensionless. And then we say that we expect it to be suppressed by 1 power of n. So let's multiply by this extra power of n. And let's see if this would be of order unity first. And independent on mode number, you see this is 200 modes. This is an inertial interval, I mean, pretty good. This is a direct cascade and inverse cascade. This is a direct cascade, this is an inverse cascade. Okay, so you see here is that no, this is a direct cascade. So this is the dissipation region, and this is the dissipation region here. So you see that for m equals 3, this is for the unity, for m equal 4 is for the unity, it's essentially the same. There are 2 different cumulants for m equal to 4, and you see that they're actually comparable. And we see that the probability is scale invariant in the sense that as long as we are inside the inertial interval, the non-Gaussianity, which is usually we see as an anomalous scaling, we see it as an intermittency which increases as you go away from the pumping. Here it's only in the damping region it really rises, and here rises. Along the inertial interval is practically constant. And for higher order cumulant, it's also practically constant, you see here, which means that it's something which I haven't seen before. It's a scale invariant, very non-Gaussian distribution. It's Gaussian as long as you look at a 1 mode, at 2 modes, at 3 modes, because then you would kind of, it's marginal distribution, you integrate over other things and it's close to Gaussian. But here you can see it for even higher, for m equal to 6 and for m equal to 7 and 8. It's more or less scattered. It's very difficult to get good statistics, as you probably guess, from for 8th order, for cumulant, which is a correlation between 8 modes related to different wave numbers. But still, you see that it's independent on the mode number, which means that it's kind of scale invariant. On the other hand, they all for the unity. Well, actually, probably because this I still don't understand very well. There is some factor. This is already non-dimensional, so you're supposed to be everything for the unity, but some higher moments have factors like 5, 10, or 20. They are probably factorial factors which you need to take into account just due to combinatorics. But the conclusion is unmistakably the confirmation of what we expected from Hopf equation, that the cumulants do not decay with the number of cumulants. Turbulence is characterized not only by the third moment, which is a flux 3-mode correlation, but by a correlation of all modes inside the inertial interval of a comparable size. And of course, then we went back to our this work with Michal, and we asked, okay, so what if we have a weak turbulence, where really we have, because this Fibonacci model is like incompressible turbulence. It's only resonant interactions. There are no small parameters of nonlinearity. But in this case, again, it's you can compute in a standard way third moment, and then you can compare Gaussian distribution with the true distributions that you would expect dynamically, and it's characterized by relative entropy. And then you compute relative entropy through the cumulants, and then you find out that in equilibrium it is uniformly small, and in non-equilibrium it is actually growing within the weak turbulence theory, which means that there is no weak turbulence solution. The solution is really far from the turbulence, and that's again unpublished numerics. Here we have a third model. This is for capillary waves. With turbulence, and here you see that we take 2 modes here and here, and see with which third mode it's actually have this non-trivial cumulant, which would be a flux. Its imaginary part would be a flux, and you find out that here is the maximum, which is resonant as you would expect. And then you raise nonlinearity. The left and right are different levels of nonlinearity, and up and down is third moment and fourth moment. I don't think anybody ever looked for fourth moments, and this is cumulant. This is something which has no reducible part, right? And surprisingly, you find of the same level, color code is the same. So it's small, but it's noticeable. And the fourth order cumulant is of the order of the third order cumulant, which is a flux in this case. So even though I don't have any analytic computations in this case, it's probably doable, and we're going to do it. But again, but what we see for fourth order cumulants is they are a resonant point is noticeable. So here is this mode, that mode, and that mode, and we ask with what else they correlate. And here is the resonant, but they are mostly correlate with a point which is kind of symmetric to this resonant and to these points which are more or less on the same frequency line. And at high nonlinearity, you see that this resonant is getting more prominent. So the non-resonant kind of more or less blur away. So at this point, I would like probably to go into, again, you can look at the mean value of the phase difference. Again, this is a weak turbulence with several thousand modes, I guess. And then you see that this is indeed the phase difference for which is non-zero. So if I now go into the conclusion, is that this shell model, which we call Fibonacci model, because it's a Hamiltonian and it has a Fibonacci a set of integrals of motion, indeed it has a case where equilibrium and turbulence has naively the same scaling. If you're interested in occupation numbers, they are practically indistinguishable. And as you increase inertial interval, they are just like everywhere coincide. But the moment you start looking into higher and higher correlation of modes, you see that they do not diminish within order. So there is something which most likely is related to the fact that all, which I believe, that the non-equilibrium probability distribution are essentially singular in phase space. And so they are characterized by arbitrarily strong correlations. So it's probably that some kind of perturbation theory is possible, but it's clear that we are dealing with a non-analytic perturbation theory. So the passing from Gaussian thermal equilibrium to even what looks like weakly non-equilibrium, because the flux is numerically small relatively to the second moment, it's a non-analytic transition. So you need something which would account for this fact, and it's still not known what it is, but at least the naive idea that I can handle it more or less like Wilson did it, it's a lot of miracles which happens when you do perturbation theory for thermal equilibrium, and you do not notice them until you start trying to do it out of equilibrium, and then you find out that all the beautiful properties that you were kind of using, they disappear. And that what, of course, Dorfman and Cohen found for dilute gases, that if you start doing it for virial expansion, for equilibrium, it works nicely. At every order, you can get equation of state. But for non-equilibrium, you get divergences. And I think that this multi-mode correlation, which we found, they are a reflection of it. For dilute gases, people actually built a renormalized perturbation series that were able to take it into account, which is, of course, much simpler problem technically than what we are handling now. And they were only interested in a weakly non-equilibrium situation like computing viscosity. But it may be in this case, we'll find it out, but it's clear that it will be still long and winding road. So let me stop at this point and take the questions. Thank you.
Thank you, Grisha. So we have time for one or two questions. Truba, yes, please.
Hi, Grisha. This was too fast for me to follow. I just want to ask about one aspect. are you saying that the weak turbulence theory is not really accurate?
The statement which was actually made before is that weak turbulence is weak as long as you are interested only in a pair correlation function. Then wave kinetic equation works pretty well even for turbulence.
Okay.
But the moment you're interested in multi-mode probability distribution, it's not close to Gaussian.
Excellent, thank you.
And the same true with the Fibonacci model in the case where it seems to be close to equilibrium. It isn't.
Other remarks or questions?
Okay. Yep, I will probably scare people away. But I guess the conclusion, at least the last line, is the main take-home lesson. That we never considered non-Gaussianity from this viewpoint. And it's actually, I think that's where the essence of turbulence, not in anomalous scaling.
Okay. Okay, so maybe we can switch the screen and.
Okay. So I stop sharing.
Yes, Grisha.
Okay.
Yes, please. Thanks a lot.
Yes.